Hello everyone, my name is Daniel and I'm a programmer and an artist, and my last video was about array and deformer nodes, and there was a comment on there asking if you could do an array where each element in the array was a random object from a collection or something like that, and I thought that could make an interesting video. So that's what I've got here. I've got a node group that makes a random array, or makes an array where each element in the array is picked randomly from a collection. This isn't a node that comes with my geometry nodes assets yet. I might add it in the future, but for now it's just a tutorial about how you could make a random array. So this node group also has all of it works on curves, and so it has all the sort of curve deform options as well, where it tries to make an array of objects that fits the length of the curve and works on multiple curves of various lengths and stuff. You could also, that's what this part up here does. You could also stop halfway through and just make an array, a straight array along an axis or something. So let's go ahead and get started going through this. All right, first thing we have is our collection info node. That just gets the collection of objects we want to pick randomly from the instance along the array. And then we want to know how many instances there are in that collection. So we get domain size of the instances, and we take our instance count. So then we're going to take our instances and our instance count, and we're going to use that down here to calculate and store the sizes of a bounding box size for each instance in that collection. So here we have an index. The index is coming from this capture attribute node on the points, so the vertices of this mesh line. So indexes are tricky because you always have to figure out what the domain is that they're working on. But this is an index of a vertex on this mesh line. So we're going to create a mesh line with a number of vertices equal to the instances in our collection. So there's 3 instances. We'll make a mesh line with 3 vertices. Then each vertex, so the vertex at index 0 is going to be essentially paired. This mesh line is basically some memory where we can save bounding box sizes. And the first vertex in that mesh line is going to be paired with the first instance in our collection. So we're going to capture a value on those vertices where the value is the size of the instance bounding box at the same index in the collection that the vertex is in the mesh line. So the first thing is we need to know something about how the bounding box works. And the first thing to notice is that it outputs a constant value, not a field. It doesn't have the diamond shape, it's circular. So if we were to realize this first, if you view this, you get one bounding box, so one cube-like shape. If you plug instances into it, you actually get 3 bounding boxes, but you only get one value. So I don't know what it is. It's probably the last one or the first one. I don't know. But we can't plug this into field socket and get different values for different instances. So we have to be a little more clever about it. So let's go in this group. So then we're going to use the bounding box node to get 3 bounding boxes on our instances. But those bounding boxes are still instances, which is kind of funny, but we're going to realize the instances. So now we have a mesh with 3 cubes in it. So now we have to think a little bit about how a mesh is structured. So let's take a look at this. We're viewing the index of our vertices, and we're looking at the first index. And you can see that the first index in our geometry is this one here. And you can see if we hover here that the geometry has 24 vertices in it, because we have 3 cubes, each with 8 vertices. If we go through this, we can see the first vertex is here, then the second one's over here, third one's over there, fourth one's here, 5, 6, 7, 8. So vertex 0 is in the negative direction on every axis. So you can see the y-axis points this way, the x-axis points this way, and the z-axis points this way. So this vertex is in the negative direction on every axis. So the position of that vertex would be equal to the minimum of the bounding box. And then the vertex, the 8th vertex, their index 7, is in the positive direction on every axis. So the position of that vertex would be equal to the maximum of the bounding box. And you can also note that the first 8 indexes are all the same cube, and then the next 8 are the next cube, and then the 8 after that are the third cube. So using that information, we can go through the first 8 vertices of the mesh and know that that corresponds to the bounding box of the first instance we passed in, and that then the vertices from index 9 to 16 would be the vertices of the bounding box of the second instance that we passed in, and so on. So the first thing we want to do is some math on our index. And we want to divide the index of the vertex. So this is the index of the vertices in our mesh. We want to divide that by 8 because every 8 vertices corresponds to one index. Because every 8 vertices corresponds to one instance. So if we divide the index of the vertex by 8 and then floor it, 0 through 7 will all equal 0, and those are the vertices of the first instance we passed in. And then from 8 to 15 will equal 1, and those are the indices of the second instance we passed in, and so on and so forth. So then the number coming out of this floor is identical to the index of the instance instead of being the index of the vertex. Then we also want to do the index modulo 8. So that will still count up by 1 each time. So the first 8 vertices, their index will be identical, 0, 1, 2, 3, etc. But then once you get to the 8th index, it will repeat back to 0. So then we get an index where each vertex in the vertices in the same corners will share the same index. So all of these 3 vertices here will be 0 because they're all the first index in their set of 8. So once we have an index that's consistent through every single bounding box from our instances, we can just check which vertex it is. So we want to know the 0 vertexes and the 7 vertexes because they're on the minimum and the maximum sides of the bounding box. And then we can just multiply the position of all of the vertices by the result of that Boolean check. So then we have a vector that's 0 on all but 3 of the vertices, 0, 8, and 16. And the same for this one, but it will be 7, 15, and 23. So then we can just do an accumulate field with that value where we group the accumulations by the index that we calculated of the instance, where we converted our vertex index into our instance index. So then for each instance in the collection, there will be a different value calculated for each of them, and we'll just store that value on all of the vertices. So now you can see the first 8 all have the same value, the second 8 have this other value, and the third 8 have a third value. And we can store both of those on the geometry. Then we can get our index from the group input, which is the index of a vertex in this mesh line coming in here. So that's going to be 0, 1, and 2 in this case because we have 3 instances. And we want to multiply that by 8, which basically converts it from an instance index into a vertex index. So now we can sample the first vertex of each bounding box. And then we can just use that to sample the index of a point on the geometry of our bounding boxes. And we're going to pass our 2 values we captured to those sample indexes. Actually, I don't even know if you need to capture these, but I did, so I'll leave it like that. So then just as a useful tool, since we're probably going to want to do it later, we can subtract those values from each other. So we can take the maximum value minus the minimum value, and then the result of that is going to be the size of the dimensions of our bounding box. And that's our bounds at index node. Once we have those calculated, we can just do a capture attribute on our mesh line to save the size values, and then we can do an attribute statistic on the points to get the average size, which we can then use to guess how many elements to create. So this axis picker node is another node that's in my arrays and deformers blend file. It takes in a number, 0, 1, or 2, and then it splits a vector apart into one axis and the other axes, depending on which one you picked. So just to briefly go through it, it's we check if the input number is equal to something, then we scale each channel of the vector by those Boolean values, and then we add them together and output that as like a length value. And then we combine them together into a vector and output that as the axis. So it's the same as the input, but with only the selected component kept. And then if we subtract that from the original vector, we can get the other axes that aren't the one that we picked, which can be useful. So I use this axis picker node quite a bit to allow you to make your arrays go on the X, Y, or the Z axis, depending on what you're trying to do. In this case, we're just going to take the value of it to figure out how long that average is in whatever direction we picked. So it's 0 right now, so we picked the X axis to keep. So how wide is everything in the X axis is what we're asking, essentially. Then we're going to use that up here to calculate the size. First, we want to know how many splines are there in our curve object. So right now we have 1. This would make it 2 splines. We're going to create a vertex, so a mesh line with a count of 1. We're going to create a vertex and then duplicate that vertex times the number of splines there are. Then we want to capture the duplicate index on those vertices because we're going to use that to assign those vertices to different splines later on. Then we want to sample the spline from our input curve object at the same index as the duplicate and get the spline length. And then we want to capture that attribute on our geometry that's just one vertex per spline. And then we want to use that value we captured on our vertices, and we're going to divide that by the average size on the x-axis of our bounding boxes. So this gives us a count of how many average objects it would take to fill the spline. And we're going to round that to turn it into an integer. And then we're going to add this adjust length estimate value to it so that we can, if the estimate was too short because the average is smaller than the objects, since if the average is bigger than the objects it actually picks, there won't be enough to fill the curve, so we can fix that by adding some extra ones. And then we're going to duplicate our vertices again, but this time the amount's going to be variable depending on how long each spline is, and it's going to be the count we calculated based on dividing the length into segments the size of our x-axis in this case. So if we view this, you can see that we get a bunch of vertices, and at some point here the count resets to 0. So this is for the second curve that's shorter, and this one's for the longer curve. And then if we viewed this value up here, you can see that they'll all be 0 up to 66, and then they'll turn into 1s. So that's which spline those points are assigned to, or will be assigned to, I guess. And then we just have to duplicate our instances. So this comes all the way from back at the beginning from our collection info. That's the geometry. We want to pick instances, and the instance index should be a random value between 0 and the domain size of our instances minus 1, because the random value includes the maximum in the selection. So now here, if we were to view this and look at instances, you can see that we have 91 instances of random types, or of random objects. And then we want to capture an attribute on that we never use. Let's get rid of that. Anyway, the next thing we want to do is array these along the x-axis, or whatever axis we pick with our axis enum. So we do that with a set position node, but we got to figure out what the value we should be putting in this position socket is. So let's take a look at that. So we're going to use our bounds at index node again, but this time the instances is the same. It's our instances from our collection. But the index this time is going to be the random value that we used to pick which index to spawn on the points. So that value will match between these two. And then we're going to take the size vector from that into an accumulate field node. and we're going to and we're going to accumulate grouped by our spline index. So each spline will get a different increasing count. So then at the first instance in our group, this will be 0, and then the value will grow. I think this probably only works if the origins of your objects are at the center. But we have 2 objects, and they're of different sizes. And we want to try to offset them so that the bounds of each object touches the bounds of the previous object. And the way we can do that is by noticing that the size of this from the centers is half of this object's size plus half of this object's size. And therefore we can deduce that that's also half of this total size. So if we just add these 2 sizes together and then divide that by 2, we'll get a vector that's the same length as the vector we want to know. So we can just do that here. We can take the leading and the trailing vectors from our accumulation, we can add them together, scale it by half, and then multiply that by the axis that we picked. So if we pick a different axis, it will stack them in a different way. Once we have that single axis vector here, we can set the position of all of our instances. Then we can delete some geometry, and the geometry we want to delete is the instances where the length of the accumulated field at that instance is greater than the length of the spline. So that takes us from this overestimated array of objects to one that's as close as possible to the actual length of the spline. And then we can turn those into a mesh with realized instances. So now we have, in this case, 2 arrays of objects on the x-axis. You can kind of see them overlapping here. 1 for each curve in our spline. All that's left to do then is to take those arrayed objects and make them match the shape of our curves. And we can do that with another set position node, this time on the vertices of our objects. And we're going to calculate 2 things on that. We're going to calculate the position first, and then we're going to add an offset to it. So let's look at how we get those vectors. So all the way back here, we have our group input with our curve input geometry. And we're going to sample that twice. First, we're going to sample it to get the length of the curve. And then we're going to sample the curve to get the position, the tangent, the normal at a specific point through the curve. The point that we get, it depends on this factor value, and the factor value should go from 0 on the one end of our array up to 1 at the other end of our array. And the way we can calculate that factor is dividing the x position of the vertex by the total length of the curve. It won't be quite perfect because I don't actually know exactly how long this array is, and I haven't thought of a way I can calculate that. But so you can't squish it so that the last vertex perfectly lines up with the end of the curve, but it'll be pretty close. What we want to do here is we want to take our spline index that we captured all the way back here when we duplicated the vertices the first time. And we want to take that to sample an index on the spline of our input geometry where we get the value that's the length of the spline. Once we have a value that is equal to the length of the spline that the array of instances is assigned to, we can use our axis picker again, to like this time on the position, to get a value that's the position along the axis that was chosen. So in this case, the x-axis. And we can divide that position along the x-axis that the vertex is at by the total length of the spline that it's assigned to get a number that's approximately between 0 and 1 to use in the factor of our sample curve. So then we want to sample the curve index, that's the spline index that again we assigned to the vertex all the way back at the beginning. And we want to sample the factor that we calculated for the vertex depending on where it is on the x-axis. And then the value that we want to know about is the radius, so that we can use the scaling feature of the curve. Once we have all that, it outputs a bunch of information we can use. Here we have the radius of the curve at that point. We have the exact position and world space of the curve at that point. We have the tangent direction at that point, and we have the normal direction at that point. If we take the cross product of the tangent and the normal, we get the binormal. So that's the tangent goes like this or something. The normal maybe points in this direction, and then the cross product of those two would point perpendicular to both, so up in this case. So then those are going to be the three axes that we used to calculate the new position of the vertices from our input array. So we can first just take the position and plug that straight into the position of our set position node. So that looks like this. It ends up with a very thin line of geometry that basically follows the curve. Then we want to push the vertices away from that center line where the y-axis of our input array equals the normal and the z-axis matches the binormal. So we can do that by using our axis picker on the position again, but this time we can add 1 to our input number and add 2 to the input number, and then do a modulo 3 so that we get the next two numbers no matter what input was picked. So say we picked 2 because we wanted to array along the z-axis. Well, then 2 plus 1 equals 3, and 3 modulo 3 equals 0. So this would equal the x-axis in that case. And if you added 2 modulo 3, it would equal 1, which would be the y-axis. So once we've extracted from our position in this case, the y-axis and the z-axis, we can scale our binormal and normal vectors by those amounts respectively and add them together to calculate a new position that's based off the tilt of the curve. And then we can scale that position by the radius, which is the value that we passed through our sample curve. And then we can apply that to our set position node as the offset from the center position, which gets you this. And here you can see how the length of the array isn't quite perfect and we're kind of squishing this object. There's a bunch of vertices stacked on top of each other at the end here. And then if you make it longer for a little bit, it doesn't quite reach the end. Anyway, it's pretty close though. Would work pretty well for most things. It's only if you wanted to be super precise that it would have some problems. I'll have to do some more thinking if there's a way to calculate the actual length of that array easily. But yeah, that's it for now. Hopefully I explained this in a way that is possible to understand. It does get a little bit complicated. Sometimes I'm not sure if it makes any sense at all. That's how you could do a random array of objects on a curve, or a array objects along a curve where each element is picked randomly from a collection. Obviously, you could probably add a lot more to this, like being able to merge if you arrayed things that were where all the ends matched up. I don't know, you could add all kinds of stuff to it if you wanted to, but which is why I haven't made it a no yet, because I'd probably want to add more options. I'd probably want to add maybe something to do with UVs to it. I don't know. But as far as a basic node that does a random array, it works. But yeah, that's all I've got for now. Hopefully it was interesting and understandable, and thanks for watching.